Um, so just to start off, we're done with the part two now. We finished the project. Um, I'm I have mixed feelings about this chapter and how the total project ended up turning out. Um, my personal opinion is it seems like we added some kind of unnecessary complexity with all of the different models and the ways the data is handled and everything. But I think it's a good showcase for what a complex pipeline might look like. Um, so that's my general review for part two. Um, did anyone have any aha moments or feel like it all came together in this chapter?
I think he made a couple of interesting points, like for example, the one about splitting your data into three, which is what I was taught ages ago, but he hasn't talked about it. That I think was a really good point in terms of data leakage. So I think he made a couple of good points, but I kind of agree with you, Ryan. I kind of felt like there was a lot of labor in this chapter for not a lot of gain.
Yeah. They were kind of showing the stitching together, but they skipped over quite a bit, and then the actual end product, it didn't the pieces didn't necessarily fit logically in my head altogether. um, but anyway, getting into the actual contents of the chapter, so the focus was that integration, figuring out how do we piece together this segmentation model we trained, and how do we put that together with the classification model. Um, so we start in the first section, and so they're basically just laying out, here's our goal. We need to fit these two together in some way so that the segmentation figures out what we're looking at and the classification figures out, is this a nodule or not? And so one is really just kind of recommending to the other the areas that it's interested in. Um, and so in the second section, they're talking about the validation set and the potential problem in that in one of the models, we were validating based on the list of nodules, and one of them we were validating based on the CT scans. So a CT scan could, in theory, have multiple nodules, and then all of a sudden that screws up our validation where we have um, multiple nodules per CT scan, and then all of a sudden our indexing is off, and then we don't have the same matching between the two. And so the way that these kind of mismatches typically manifest is you look at your metrics and all of a sudden you say, wow, we have 90% accuracy, whereas before we had 80%. So you'll get this artificial boost in your score. And then you have to look at that and you say, why does that happen? That doesn't really make sense. Why is it turning out better at the end of this pipeline versus when I was just giving it the pre-filtered input? Um, and so that's one of the common things in a machine learning pipeline. You need to figure out how exactly to lay out the validation set to make sure that you're not accidentally leaking information in some way. Um, I don't remember if we talked about it, but one of the other potential gotchas in this scenario that I've seen in some machine learning problems is even across CT scans, if you have the same patient, for example, if they got multiple CT scans, you can get overexposed in that way. And you can say, okay, well, out of the 153 that showed up as nodules, actually, there's only half that amount because most of the people got two CT scans for whatever reason. So just another thing to keep in mind. And then on the next section, looking at actually the implementation of bridging that gap, what they were talking about is taking the CT scan, every single slice of it, so the different depths, and then passing that to the segmentation model. And that segmentation model is trying to tell which pixels are of interest, basically. And so the actual physical output of that is predictions from 0 to 1. So we were using that sigmoid layer that constrains it to be between 0 and 1. And for each pixel, it's telling us, is this a nodule or is this not a nodule? And then eventually we want to stack these all together back into the original image. And then we want to put some threshold on it. So these are continuous outputs. It can be 0.1, 0.2573, whatever. And we want to eventually make a hard judgment of, is this a nodule or not, this specific pixel? And so a good default is 0.5 because our model is directly trying to optimize towards 1 and 0, and 0.5 is in the middle. But if you have some other some metric that you're focused on, then you can kind of tune that based on the threshold. So you can set it higher if you care about one metric more than the other, or the opposite direction if you care about a different metric. One of the tricks that they talked about is you can use erosion. And so what that's essentially doing is it's looking for isolated pixels and will generally try to diminish them. So there's a good example in the OpenCV library. You can look at erosion, which is making it slightly smaller, and dilation, which is making it slightly bigger. And they have a good handwriting example, and you can basically see the erosion makes the cursive I slightly thinner, and the dilation makes it slightly fatter. And so what the erosion does here is it can take small disconnected pieces and it can essentially just make them go away. Because if it doesn't have lots of interconnectivity, if it's not next to other pixels, then it will just go to 0 basically. And so that's good for this case because we might have just a stray pixel that lights up, and we don't want that being a region just because one pixel for whatever reason showed up. It might significantly contribute to our false positives, because we always know that these nodules are typically a lump of connected pieces. And so the next piece they were talking about, we can use this SciPy ND-image measurements.label, and that will find the connected pixels and give us the actual returned array for them. That's not something I've used in the past, so I don't know a ton about that one, but I sounds like an interesting tool potentially. And then another one is looking at the center of mass. So now that we have that blob, we can say where is the actual central pixel inside of that. And so that will correspond with the original labels that were given to us, where we were told basically this is the center of the nodule, and then here's the dispersion around that. And so one of the things they were showing is in this pipeline all along the way, we're essentially eliminating pieces of irrelevant data. So we start and we've got the segmentation, and in that we have all of these pixels that we don't care about. And so the segmentation model can eliminate some certain factor that helps us focus. And then beyond that, once we have the connected slices, then we pass that to the classification module. And then that module will determine nodule or not a nodule. And then even within that, we can then try to make the classification of benign or malignant. And all the way down there, we're doing some sort of compression, basically saying, here's what you need to focus on. Here are the points that are the samples that are important. And so that's a good way of thinking about most of these pipelines, is you're constantly doing this elimination, and you need to figure out which piece is actually failing in terms of the elimination. So in the next section, they're talking about quantitative validation. And so they actually run the validation set. They find that out of 154 actual nodules, they captured 132, which is pretty good. And then they look a little bit deeper and they say which ones were missed because of the classification module and model, and which of them are missed because of the segmentation model. And they find that of the 22 that were missed, 13 of them came from the segmentation model. And so the classification model didn't even get a chance at looking at these because the segmentation model already filtered them out. And so that's probably a good place to look as a starting point, because we don't want the segmentation model to block what could be a good classification model, just because it wasn't even given a chance to look at those things. And I think that that's generally a good process to follow, to look where in your pipeline is the failure, what kind of way is it failing, and then dig in and focus on the thing that actually matters. I think that that's one of the biggest failures I see from new people who are trying out problems is they look at the final metric and then they say, I need this number to go up. And then they brainstorm about how do I get this number to go up? And they say, I'm going to do this new architecture. I'm going to do regularization. I'm going to do augmentation. I'm going to do something else. And then it turns out you look at those samples and the input's just blank, or something else is critically wrong, or a failure's at this place and they're working on this other place. And so it's really, really, really important to actually look at your models and look at the pipeline and understand where the things are actually going wrong, because you can spend a whole bunch of time and be trying to solve a problem that's unsolvable because you've already missed some of the inputs potentially. And then beyond that, they were talking about the possibility of trying to determine malignancy. And so in this, they laid out just a original baseline saying, let's just look at the diameter of what we've discovered and see if that has any relationship with whether it's malignant or benign, with the theory being that more larger mass is probably more likely to be malignant. And so what they did is they get the output of the model saying, here's the size of this mass, here's the diameter, and then they just do a threshold sweep. They say basically, let's try everything that's under a millimeter, everything that's under 2 millimeters, everything that's under 3 millimeters, or even more granular steps than that. And they're assessing how many of these are we correctly classifying? What does our confusion matrix look like? And then they showed this sweeping graph essentially showing here's our F1 score as we sweep through all of these values, and you can pick a value that is most optimal looking at that graph, or just analytically picking whichever one shows the highest in terms of your metric. And so this is a really useful trick that I've seen in a lot of competitions. And you can apply that in a lot of different places. So we were even talking about that 0.5 threshold in terms of the segmentation maps. You can do that there as well. You can say, basically, I'm going to sweep over some region of values and determine what is actually best for determining the malignant or the nodule, not a nodule threshold. And so that's just a trick that I highly recommend you add to your playbook, is figuring out thresholds can sometimes be the crucial step, because it's not guaranteed that your predictions are directly aligned on 0.5 or some other nice value. And in this case, you don't even have the option of a default, because you have to look through the whole range of 0 to 12 millimeters or whatever it was.
I have a question here. It's more probably a thought than anything else, if I can interject for a second.
Yeah.
So this makes me wonder whether, and I think as a first pass, what you're trying to do is you're trying to match the same accuracy as a human doctor, right? A human interpreter. But it also makes me wonder that if we went through this and it basically comes out, let's say, for example, it says anything smaller than 5 millimeters, we can kind of ignore because it's not likely. I think what you might be doing is you might be building in, I'll use the word bias, for lack of a better word, just simply, this is as good as a human does. And humans, for whatever reason, tend to pay less attention to things that are small versus things that are big. So you're only building a model that's going to be as good as a human, whereas perhaps you have the opportunity to build a model that's better than a human if you're willing to look at things that were smaller. But you're limited by the fact that the average human only considers things that are 5 millimeters or bigger, just because there's too much information, et cetera, et cetera. So I was wondering whether this is actually, I think this is a fine approach for equivalence to human, But if I was thinking about being able to beat a human, I might not necessarily pursue this. I mean, what are your thoughts about that?
I think that at the end of the day, you're always going to be limited by the noisiness of your labels. And I think what we have here that's good is they have 5 different doctors who have made judgments. So in theory, you can make some trade-offs. But if systemically across the board, all 5 doctors are always missing some smaller sized mass, then there's no possible model. Even just looking at thresholds, even looking at the fanciest CNN architecture, if your labels never correctly find those, then you have no hope, basically. So the quality of the labels is really paramount to actually getting anything useful out of it.
Yeah, okay, good point.
Hey,
So
Ryan, just one other side comment. So when you talk about sweeping through the values, so if you take your predictions and you sort them, by the probability or whatever, of your prediction, if you sort them from lowest to highest, then whatever the sweeping thing through that you're doing, if necessary, that can always be computed in linear time, even if you had a ginormous data set. So if it's small, then you don't even have to think about how you do it. You can calculate it inefficiently. If it's square time, it's not going to hurt you. But I just wanted to throw that out there. So if people are thinking about doing this, just sort your data, and then you can do these things very efficiently.
Mm-hmm. Yeah.
It looks like it would be better to label all the data after biopsies. Then it could be more useful than doctors. Oh well.
Mm-hmm. Yeah.
Yeah. In that sense, this part 2 is not terribly realistic. I mean, Ryan, you were commenting. To me, it's sort of like, well, this is learning PyTorch, and they've sort of blurred into trying to teach data science, I felt. But then they're teaching data science somewhat superficially. And so it's like, I don't know. I felt like they could have spent less time and just sort of said, here are some things that you'll need to do in a more complex scenario. You need to glue models together. You'll need to do this. You'll need to do that. And so here's some of the code building blocks in PyTorch, how you would do those things without necessarily spending as much time talking about, rock curves and things like that.
Yeah. So after the thresholds they were talking about, so how do we actually go beyond this? How do we maybe do better than just picking a threshold and then calling everything below a certain point benign? And so we can throw another CNN at it. We can say, okay, now let's take a look at the ones we've classified as nodules, and let's classify them as benign or malignant. And so they started off saying, we have so little data here, maybe we can start with a pre-trained model and we can get benefit out of that. And so the benefit here is we're starting with some knowledge about edges and whatever else is captured in these pre-trained models, and maybe it will do a little bit better at just classifying benign or malignant, even though we have so little data here. And so they start with an initial approach, which is we have this pre-trained ResNet 18, for example. It's been trained on the ImageNet data set that we talked about several weeks ago. And then what we'll do is we cut off the last layer and we just put on our own layer, and we use that first part frozen. So we don't update any of the weights. It's just outputting essentially these anonymous features. And then we're training a simple network at the end that is just saying, given these features, how do I make a mapping to benign or malignant? And they show that it eventually converges to a similar conclusion to the simple cutoff approach. And then they look at the training loss and they figure out, well, it turns out it looks like our model does not have sufficient capacity to actually make anything really useful out of this. And so they decide, let's take our model and let's unfreeze those first layers that are just generating those features for us now. And let's actually train that portion. And so then they train the entire network end to end. And it turns out it does a little bit better, but not really anything groundbreaking. And then they kind of come to the assessment, maybe with the inputs that we have and the labels that we have, maybe this isn't exactly solvable, at least in current state. Maybe there's ways to improve upon it, but not with obvious techniques. And so in the next section, they're talking about how do we actually piece this whole thing together. They skipped over a whole ton of code, and they just said basically just put the square block into the round hole and then everything's good. In the real world, this is going to be much more difficult because you probably didn't intentionally design the entire thing to run as a single script right from the onset. So just a fair warning, in most projects, it's not going to be this simple. If you have model A and model B, you're going to have to write some connecting code or say, write this to a file and then this other model picks it up or something like that. So in their scenario, you basically just put a different setting in and then it says, okay, now I'm just going to run the whole thing. And so in the end, they look at the metrics a little bit and they put a little caveat in saying that in this validation set, we've done early stopping, we've selected methods that specifically optimize for this holdout validation set. And it's a fairly small validation set, so we can't be 100% confident in the validity of this validation. We know that there's going to be a little bit of variation. And if we actually apply this to some new unseen data, we might see slightly lower results than what we got on the validation, because the validation, we specifically stopped the number of epochs, we specifically changed the algorithm, we specifically iterated multiple times in order to optimize for that value. And so the test set might show up with lower numbers than we get from the validation, just something to keep in mind. And so the recommendation there is, if you have enough data, take a third split. So what we've done throughout the book is we say, here's our training data, here's our validation data. Maybe you also make an additional holdout set with the test set, which will basically function as, we'll optimize for the validation set, and then we will actually take our numbers from the test set that we haven't optimized for. And in theory, those should be better representative of what it would be like on unseen data. In this scenario, I think it's a little bit tricky because we do actually have a wealth of data, but we don't have a wealth of the condition that we're looking for, the nodules and the benign and malignant tumors. So you can split the data a third time, but you can get very unlucky and it can turn out that you have 0 nodules in that small test set that you hold out. So you're trading off a lot of different things there. You kind of have to be conscious of the splits that you're making. So in the next section, they were talking about, what do you do once you finish this whole thing? And so typically the thing is, well, the accuracy isn't good enough, or I want to do a little bit better on something. And so one of the things that they stated is you need to make sure that your validation is solid first. So in the first layout, they were doing 1 in 10 samples is going to be put in the validation, but they showed, since that's only 100 or so nodules, you can get variation between runs, and it can be 150 versus 154. Is that significant? Is that actually better? It's kind of hard to say. That's just a small margin. And you can do some studies and say, well, statistically, I think that this is better, but it could be better because of just a lucky seed, or it could be better because of a number of different things. You can't necessarily say, oh, I added an additional layer and now it's better by 2%. You can't really confidently say that. And so they said, maybe you switch to 1 in every 5. So you do a 20% validation set instead of a 10% validation set. And then once you know that you have a validation set that is actually significant, you can look at different techniques. So the ones that they laid out are better regularization. So that can be the actual numerical regularization that we talked about, L1, L2, and different variations of that. You can add dropout. And then you can also do that with augmentation. So the stuff that we talked about, the different techniques that they laid out. And then you can also do label smoothing, which is essentially right now, all of our labels are zeros or ones, and label smoothing gives you something slightly in between that. And there's been some results that show that that can be better in some cases, because the way our losses are typically formatted, you get heavily penalized if you get a result that is near zero but should have actually been a one. You get a massive spike. But if you say you guessed a zero and it should have been a 0.9, then your result is slightly less aggressive. You won't be penalized. And so label smoothing is typically good if you know that you have some mislabels in your data, because you won't be massively penalized for something where your model might have been actually correct and your label is wrong, but you get penalized and then it ends up hurting your network in some way. So label smoothing can help in that regard. And sometimes I would say in my experience, I haven't had great results out of it. I just haven't seen it mathematically change all that much. If you're doing a threshold search at the end, all that's going to change is how confident your results are, not necessarily the actual quality of the results. But that's just my experience. I'm sure there's some scenario where it's been beneficial to someone. And then after that, they talk about ensembling. So bringing in multiple models. So you say, I've got one segmentation model, it's pretty good. I'm going to just do 10 of them on different subsets of the data, or all of the data with different variations of the model. And then you can average those together, or you can do some voting algorithm, or you can do various different ways to combine them. And you can end up with something that is better with multiple judgments versus just an initial. And so this is kind of similar to how we're doing aggregation across multiple doctors for the label. We might do aggregation across multiple different models for the prediction. One of the other things they laid out is multitask learning. So right now we have the models doing one specific thing. So it's just doing segmentation, or it's just doing classification. We could train something that tries to do both all at once. It could try to do some other task. You could basically say, one of the popular tasks that has popped up in NLP and vision and various different places is just, let's corrupt the input, and then it tries to rebuild the original input. So let's say I just take a 8x8 pixel set and just set it all to zeros. And then the model is trying to predict what those 8x8 pixels were, looking at the surrounding context. So it can say, it looks like there's some mass over here, and I'm going to try to infer what is missing over here. Maybe it's bone, maybe it's some other tissue, and it can just try to realistically recreate that. And maybe in the process of doing that, it learns a bit more deeply about what is actually in these scans and what can be expected. And then one of the other things that they recommend is looking at existing work. So that can come in the way of research papers on archive or blog posts or wherever else. One of the places that they listed is Kaggle. So Kaggle has competitions on all kinds of different things. You might find a problem that fits what you're specifically trying to do, or you might find something that is just kind of analogous. So when we were talking about segmentation, I brought up the one on the clouds. And so you might find something that's not necessarily exactly the same thing, but it might be similar techniques that you think are applicable. And you can say, okay, they figured out that this specific UNet with this filtering at the end is very successful. And so you can then transfer that and take that to your CT scans, and you'll likely have good success if it has good crossover and is good to go there and figure out some inspiration for these things. And so at the end, in the conclusion, they have this section and they basically said, here's 20 different things that we tried. All of them failed. And then we had to look at these problems and figure out some way to solve them. So they talk about the hard 10H layer instead of the softmax, and the way they did the recropping of the segmentation model, and all kinds of stuff like that. And so I think that it's good that they put that in. It would have been better if they put more detail in the process that made them come to the solution that they did, because putting it at the end, it kind of makes like, it gives the impression that we just solved this problem and we knew the solution, and that's almost never the case. Pretty much every time you're going to go into a problem and you're going to say, I think I solved it in this way, and then you come into some problem and you say, okay, now I have to change this process, or it's failing in this way, I need to change something in my training procedure. And so that's it for part 2. Does anyone, questions, comments?
So Ryan, when you talked about the multitask learning and you talked about like reconstruction, one of the things that I think is particularly interesting about that is that you can do it in a semi-supervised or even completely unsupervised kind of way. And so at least for me, I find it really interesting that you may be able to, like if it's X-rays, finding nodules, you may be able to build a network that has good feature recognition without actually necessarily even having any labels whatsoever.
Mm-hmm.
Right? Yeah. I think that I'm not necessarily usually a general artificial intelligence, kind of a guy, but it seems to me that there are a lot of problems where you don't have an ImageNet size data set of labeled data that you can then train a ginormous, CNN or whatever for a bazillion years. And so you need some other technique that's going to actually help you get some reasonable, feature extraction.
So recently there's this paper, they just put out a second version recently called Wave to Vec. And basically what it's showing is that in the task of speech recognition, so actually taking an audio and then turning it into the characters that make up the speech, they found that they can do significantly better on that task once they do this pre-task that is basically filling in the blanks of some audio. They just cut off a 10th of a second snippet and they say, what was the audio that occurred here? And one of the big problems in that domain is very hard to get labels for, while someone's speaking, actually getting, here's all of the words that they're saying at these specific time segments. And they found that of the 960 hours that they have available, if they did that pre-training task, they could get significantly further with that small amount of data that they have. And they show all of these state-of-the-art results with it. The one difficulty is figuring out a reasonable task that will get you generalized information. So you can do whatever fill in the blank task, but you have to make sure that in the end, it's going to build up some understanding that is useful for your downstream thing. And that's not always obvious how you formulate that.
Yeah, and so lately what's been catching my eye is papers about contrastive learning, and the authors do mention that. And so the idea there is, rather than cutting something out and having to figure out like what's the right way to cut it out, right? You can just say, I've got K examples where K is relatively large. And so when I see something, tell me which of these K things it is, which I admit it didn't sound like that was such an interesting task, but I guess it is. It's hard for a network to learn to do that.
Mm.
And so you should theoretically be able to do that with any kind of problem, with no matter what kind of features it has. It could be tabular data, it could be image, it could be audio, right? Basically, you're just simply saying, here's a bunch of inputs, tell me which one it's like of these K things. And if that actually causes it to generate like a reasonable embedding, that's cool.
I realize I didn't share this at any point. It's probably too late to really be useful to anyone, but I'll still link this.
Yeah, and I'll add it eventually to the GitHub, so that if somebody completely missed this week and didn't attend, or if somebody's going back and looking at certain things, they can see all of them.
Anyone have any other questions, comments on the book? If not, maybe we can try some breakout rooms if people want to continue discussing on anything.
By the way, Ryan, you talked about that Socratic thing. So I don't know that whole business about like multitask and augmentation. I don't know if that would be a topic for a session to people just talk about.
Yeah, we could discuss that.
So anybody else, any comments about something you liked or didn't like about either just this chapter or the whole book so far? All right.
So I'm going to drop, guys. It's after 1 o'clock. So I just want to say bye. So I'm not rudely just dropping off. But thank you, and we'll see each other next week.
Bye.
All right. Good seeing you. Yeah. So next week's the last chapter of the book. It's the one on deployment. So I have not read the last chapter yet.
Oh, and by the way, for
Interested to see.
those who don't know, just on a completely different topic. So I did actually go to it yesterday. What's her name? Karen defended her dissertation yesterday. Now, I don't know what the outcome was. I'm assuming it was positive, because obviously they ask you to leave the room, right? The virtual room, so that the professors can discuss and come to some sort of conclusion. But she did a pretty good job of presenting her stuff, I thought.
Thanks.
Awesome. Thanks.
Nice to know.
Yeah, that's exciting.
Okay, see you guys.
Bye.
All right. Bye, Stephen. All right. Well, I'm going to